rational exponents. So rational exponents are going to be exponents that are expressed as fractions. So fraction exponents is really what we're dealing with here. So rational exponents, fraction exponents, what we're going to talk about some tonight. So rational exponents or fraction exponents, we can simplify. It's like simplifying a square root or a cube root or something like that. So when we're simplifying, say for example, 49 to the 1/2 power, what we want to do is think about rewriting 49. And we know if we do a factor tree for 49 that that's 7 times 7, right? So that would be 7 squared to the 1/2 power. So instead of writing 49, I'm writing it as 7 squared because that's what 49 is. And now the exponent rule that we can employ is parentheses, exponent on the outside says you multiply those two exponents together. 2 times 1/2 is 1. So we're saying 1/2 times 2, and that's going to give me 7 to the first power, which is just 7. All right, so we're simplifying square a 1/2 power, a rational exponent of 1/2 out of that. Example B, a similar problem. Let's say we had 64 to the 1/2 power. We think about that. We know 64 is what, 8 times 8 is a good way to start it. And 8 is 4 times 2. 4 is 2 times 2. This 8 does the same things. So it's really 2 to the 1, 2, 3, 4, 5, 6th power to the 1/2. And then when you multiply those two together, 1/2 times 6 would be 2 to the 3rd power, or 8. Yes, I always put that base, whatever whatever I'm changing this number to, I put it in parentheses because it makes the exponent powers work right. I'll show you with your calculator how you can put in a fraction exponent with that to help you evaluate some of these things. 49 to the 1/2 power, type in the 49 as the base exponent. And then if you've got the newer version, you get it looks like an exponent, and you can type in 1/2 like that and hit enter, and we get 7. And bounce back again. This, I think this cable's gonna be an issue. I don't know what we'll do if it goes out, but we'll do something. And if we did 64, that was example 8. Though to get the 1/2 power, you're hitting the caret symbol, which is this one right above the divide sign, and then type in the fraction 1 divided by 2, and then hit enter, and that's going to work out to be 8. It won't give you that answer as like 2 to the 3rd power or anything like that. It'll give you what the number works out to be. So just be aware that may be something that comes up as we go along here. So you can evaluate rational exponents with the calculator, just type it in and work that out. So that's going to help you out a lot as you go along. Example C, say we had negative 144 and then the 1/2 power. This is a little tricky problem here because the negative symbol is just hanging out in the front. It's really not negative 144 to the 1/2 power. It's negative and then 144 to the 1/2 power. The reason you read it that way is order of operations in math says exponents happens first, parentheses and exponents, and then multiplication and division is after that. So the negative is kind of like they're saying, okay, really this problem is -1 times 144 to the 1/2. That's really what that problem is saying, because there are no parentheses around the -144. So we just work that 144 to the 1/2 out and think, okay, well, that's 12 times 12. And it's 4 and 3, 2 and 2. And this 12 does the same things. So it's really -1 and then 2 to the 1, 2, 3, 4th power. and 3 to the second power. And then the rule is when there's parentheses in an exponent, you multiply. So half of 4, 2, half of 2 is 1. So we have final answer, or next to final answer, 2 to the second power, 3 to the first power, which is -1 times 4 times 3, which is -12. And if you type that into your calculator, if you type in -144 raised to the 1/2, you get -12. Not the same if you type in -144 in parentheses raised to the 1/2. It's going to give me a non-real answer. Show mode. Change this to that. And then do that again. Which is 12i, which two different things there. I've got my calculator. If you want your calculator to be able to do that, you need to hit mode and then go down to where it says real and then a plus bi or r e to the theta I, and just change it to that middle one, right there where it's blinking there. Change it to that one, and it'll evaluate square roots of negatives that are perfect squares. Now, if you put in the square root of -72 or -72 in parentheses to the 1/2, it won't do that one because it's not a perfect square. But anything that's a perfect square, like 144 or 49, 64, 25, those kind of numbers, it can do that way.
Just press enter.
Yeah, just press enter when you get on that one, and then second mode to get back to the regular calculator screen. And then anytime you take a half power or square root of a negative number, it'll work it out with the I in there for you. So it's kind of a nice thing. And every time I touch it, I'm going to try laying it completely flat instead of kicking it up. Maybe that'll help. I think that's part of it. It's the angle. All right. So let's look at -27. Let's do a different power instead of 1/2. We've been doing a lot of 1/2. So let's do a different fraction. -27 in parentheses to the 1/3 power. So you can think about that as being, -1 times 27, and then the 1/3 power, and go, okay, well, what's 27? It's 9 times 3. 9 is 3 times 3. So 27 is really 3 to the 3rd power. And then if you multiply that both exponents, you get -1 times 3. Anytime the base is 1, it's going to come back or -1. It's going, if you multiply that -1 raised to the 1/3 power, it's going to come back -1. 3 to the 3rd to the 1/3 power is going to come back 3, and then you multiply those two together and you get -3. Have that for a final answer. We're just multiplying exponents there. Works out real nice. Questions about those? Really doesn't get much more complicated on that type of problem. And you got the calculator to kind of help you evaluate a lot of these. Okay, so don't hesitate to use it. That's why we ask that you have it. All right. Let's look at some that have a different numerator than 1. Something a little that changes it just a tad, just changes their multiplication a little bit. So let's look at one like this: 81 to the 3/4 power. Okay. So the base is 81, the exponent is 3/4. But as far as how you do that, it's exactly the same. 81 is 9 times 9, right? That's one way to get 81. You could do 27 times 3 if you wanted to. 3 and 3, 3 and 3. So that's really 3 to the 4th power, and then it's all to the 3/4. So when you multiply these two exponents together, what's 4 times 3/4? Well, the 4s are going to, it's 4 over 1 times 3 over 4. The 4s cancel, ends up being 3 over 1. So it's 3 to the 3rd power, which is 27. Yeah, that's right. And then you cross cancel. Now, I know we can type these in the calculator and get the answers out of that, but working with the exponents, if you'll force yourself to try to do that with the easier problems here, it's going to help you later on when you start throwing the X's and Y's and stuff in there that doesn't have a number that you can't put in there. So if you'll force yourself to work with the exponents by hand here, instead of relying solely on doing it with calculator, I'm not against checking them with the calculator at all. Make sure you get them right. And there's no sense in missing any of those that have just numbers. But it'll help you learn those rules and know the kind of the process that we're going to use when we start throwing the letters in there. Because the letters you can't do with the calculator. You gotta have some number sense about what's going on there to help you. So that's always a helpful thing. Even if you had something like 25 to the 3 over 2 power, even though that's an improper fraction as the exponent, it's still a rational exponent, which is just a fraction. The work is still the same. Break down 25 is 5 times 5, so that's really 5 squared. And then you just multiply that together. 2 times 3 over 2 ends up being 5 to the 3rd power, which is 125. So basic idea here is the same all the time. That's even if you have a negative exponent, something like 216 to the negative 2/3. Negative exponent doesn't really change anything about exponent rules until we get ready to fix the negatives, and we always fix the negative exponents last. So the first thing we're going to do is break down 216. I don't know much about 216. Do y'all? It's even. So that means what goes into it? 2 goes into it 108 times. And do I know something about 108? 8 go into it? 9 times 12 is 108, isn't it? Now 3 and 3, 4 and 3, 2 and 2. So I really have 2 to the 3rd power times 3 to the 3rd power to the negative 2/3 power. So again, we're just breaking that number down to all the prime factorization for it is what we're doing. And then applying the exponent rule from there. And the exponent rule is multiply negative 2/3 to both of those 3's that are exponents. So that's going to give me 2 to the negative 2 times 3 to the negative 2. Here is where we get to work with the negative exponents. In order to make those positive exponents, hopefully you remember that you move that part where? To the bottom to change it to positive. Remember doing that? It's been a while. Not something you do quite often, but if you have a negative exponent here, because they're not in fraction form, that means they're in the numerator. And to make it a positive exponent, you move it to the denominator. If it were negative on the bottom, say you had a fraction in there, if it were negative on the bottom, if you move it to the top, it moves to positive. So moving from numerator to denominator changes the sign of the exponent. And now we can work these out. What's 2 squared? 4. So that's really just 1/4. 3 squared would be 9, so it's 1/9. That's 1/36. And again, I know that you could type into your calculator 2/16 to the negative 2/3. And hit math, enter, and you're going to get 1/36. I know you can do that, but working with the fraction rules and trying to do some of that by hand is going to help you later on when you start solving those equations and doing things with variables. It's going to make it easier on you if you'll do that. Okay, so be careful of that, and try to force yourself to do that a little bit. All right. Let's get into a few other exponent rules that could come up. (18 to the 1/2 power times 18 to the 7/2 power is over 18 to the 3rd power. And we want to simplify that. So we think about exponent rules. If we're multiplying two things together that have exponents, we can do that if the bases are the same. And the base on all 3 of these pieces in this problem is 18. So when we multiply on the top, what's the rule with exponents when you multiply? What do you do with those, that 1/2 and that 7/2? Add them together. So it's going to give us 18 to the 4 over 18 to the 3rd. And now we've taken care of the division problem that's up here. We want to take care of that, or the multiplication problem that's on the top. Now we want to take care of the division problem. So if we add when we multiply, what do we do when we divide? With the exponents. Subtract. 4 minus 3 would be 18 to the 1st power, which is just 18. And on that one, we didn't even break down the 18 because we already had the same base. If the bases weren't the same, I might be tempted to break it down, but I didn't need to on this one because all of them were 18s. So that makes it a little easier to do. Let's look at this. 100 to the 3/2 times 16 to the negative 3/4. So here's one that kind of goes with that idea that the bases are not the same on this one. So that means I need to just try to work with this as 2 individual pieces and put it together at the end, hopefully. So what do we know about 100? Yeah, 10 and 10, and 5 and 2, and then this 10 is a 5 and 2 as well. Okay, and so that's going to give us 5 squared times 2 squared to the 3/2 power. And then the 16 we know is 8 times 2, 4 and 2, 2 and 2. It's actually 2 to the 4th power. Not that. So that could be helpful. Next thing I should do when I'm working with that is I see this piece needs to multiply those exponents. So 2 times 3/2 is going to be 3. 2 times 3/2 is going to be 2 to the 3rd. 4 times negative 3/4 is going to be negative 3. Now I have a couple of pieces that have the same base. These pieces right here have the same base. So I'm multiplying all that stuff together. What's my rule about multiplying and exponents when I have the same base? What do you do with them? You add the exponents. So what's positive 3 plus negative 3? 0. What's anything to the 0 power? 1. So we end up with 5 to the 3rd power times 1 because that's 2 to the 0 power. Anything to the 0 power is 1. Okay. So what's 5 to the 3rd? It's 5 times 5 times 5, which is 125. Times 1 is 125. And again, I know that you could go to your calculator and type in this problem and it would spit out 125. But working with the exponents along the way is going to be helpful if you will try to do those things in the beginning stages here, because we're about to add exponents with variables in here, and those can't be just typed in the calculator. You gotta work with that. Okay, so let's look at one that's got some variables in it. 4x to the 3/4 times 5x to the 2/5. Well, what pieces have exponents on these? The x's. This x has an exponent. That x has an exponent. What about that 4 and the 5 that's in the front? They're bases, but they don't have an exponent, or they don't have a complicated exponent. They got a pretty easy one. It's a 1. What do I do with those? Just kind of darkened in the... Yeah, 4 times 5 would be 20. Now, I know these guys have the same base because they're both x's. So what do I do with their exponents? Add them up. So I'm taking 3/4 plus 2/5. So I'm writing an extra step here that I probably normally wouldn't do if I'm working this out at home. But that's the operation that's happening. It's this stuff right here. So ever how you want to add 3/4 and 2/5 together. If you want to do the math and get the common denominator and all that stuff, great, do that. If you don't, do it this way: 3/4 plus 2/5. Enter, and then I'm gonna hit math. Enter. 23/20. So that'd be 20x to the 23/20, and that's the simplified version of that particular problem. So we can use a calculator to kind of help us add those fractions up. Nobody's going to ask you, what's the common denominator from this? Show me. You go to the food giant up here, they're not going to ask you to do that in the checkout line, probably. Now, you may not win a contest or something if there's ever one of those. If there is one of those at the food giant, y'all call me. We'll split the prize, 80-20. Go from there. All right, so let's look at another one. Go big or go home here. 5m to the 4/3 over n to the 2/3. So we've got a fraction. Let's square that fraction. And let's take another fraction. M to the 4th over 8n to the 5th. And let's take that fraction and raise it to the 1/3 power. So this is going to help us review some of our exponent rules as we go here. So what we're doing here is really refreshing our exponent rules that we've used before. As we do this stuff, we're just using exponents that have fractions in them to help us remember those rules. And so learning something new as we go there. So on the first fraction, let's work on getting it to look a little better before we start. Okay. So that exponent on the outside, order of operations says parentheses, exponents, multiplication, division out of that. So I want to take care of those parentheses and maybe do away with them if possible. What does this 2 do to everything on the inside? Times is to the every exponent. What exponents are in there? 4/3 and the 2/3, and there's one more. The 5 has an exponent of a 1. Don't forget about those. Okay, so when I multiply that out for this problem, I'm going to have 5 to the 2nd power. M to the 2 times 4/3 would be 8/3. 2 times 2/3 would be n to the 4/3. So that's just 2/1 times 2/3. That's how that's coming in. 2/1 times 4/3. Let's do the same thing to the second fraction so that we get rid of those parentheses again. Yeah, I got a fraction exponent this time. So m to the 4/1 times 1/3 would be 4 over 3. The 8 has what exponent on it up here? It's got a 1, so it ends up with an 8 to the 1/3, which we could do some work with in just a second. We know how to simplify that. That's example A and B and C, the early problems. And then n to the 5/3. Good job. All right. Now, let's work a little bit with that. We know 8 is 2 times 4, and that's 2 times 2, which is actually 2 to the 3rd power to the 1/3 power. That's what we're doing here. Is 8 is to the 1/3 power. Well, this is the same thing as 8. When I do that, I end up with that being 3 times 1/3 would be 1. So they end up being 2 to the 1st power, which is just 2, right? So I end up with m to the 4/3 over 2 n to the 5/3. So I'm simplifying that second fraction because it can. What do we know 5 squared is? It's just 25. Now I'm multiplying fractions together here. So that allows me to do all the rules for multiplying fractions, which would allow us to cancel vertically or diagonally if possible. This one doesn't do either of those. So if nothing will cancel, how do I multiply fractions? Straight across, top times top, bottom times bottom. So 25 m to the 8/3 times m to the 4/3 is going to be 25 m to the 8 over 3 plus 4, 8 over 3 plus 4 over 3. You're going to add because we're multiplying. So it'd be just 4, m to the 4th. And on the bottom, we got 2 n to the 4/3 plus 5/3 is 9/3, which is just 3. Will 2 go into 25 evenly? Evenly? No, I can't split a quarter in half. Right? It'd be tough. You got to half until the U.S. Mint starts doing half pennies. You can't do it. Okay, and it's hard to even get them to do pennies. Period. Now, if you got any pre-1982 pennies, save them. They're worth more than a cent. The copper in them. Yeah, the copper's worth more than. So that doesn't go evenly. Nothing else we can do. We're gonna stop right there. So again, knowing your exponent rules ahead of, instead of just typing it in the calculator, that's going to help you be able to do the variable stuff better. Not saying it's going to, make it a breeze, but it is going to help you do it better. If you will work with the exponents more with the numbers, when you can check them with the calculator, it will help you get better at them for the letters. Let's do one more with letters. We're going to stay with exponents pretty much all night. So, but just the kind of the context of the problem changes as we go here. And what letter we're on here? L. Y to the 4/7 minus 5. Y to the 11/7. So we have y to the 3/7 parentheses, y to the 4/7 minus 5y to the 11/7. What property does that look like? Distributive property. It looks like a problem like this, that we would distribute 3 to both pieces. It's that kind of problem. The difference is we got exponents to deal with. So it's a distributive property problem like we've done before, but we got exponent rules to deal with on this one. So we're taking y to the 3/7 and multiplying it to both of those pieces. Y to the 3/7 times y to the 4/7 minus 5 y to the 3/7 times y to the 11/7. Okay. And the rule is the bases are the same on the y's, right? So what do we do with those exponents? Add them up. So we got 3/7 plus 4/7 would be y to the 3 plus 4 is 7, right? 7/7 minus 5, y to the 3 plus 11 would be 14/7. But those fractions will reduce nicely because 7 divided by 7 is 1. And 14 divided by 7 would be 2. And that ugly problem that we started off with turns into something that's semi-decent as far as it looks a little bit more digestible. So dealing with the exponents with variables, you still got to do those rules. So if you're multiplying, you're adding exponents. If you're dividing, you're subtracting exponents. If you have parentheses with an exponent outside, you're multiplying those exponents. That's the only exponent rules that exist. So those three things are really the things that you need to be able to do. Okay. All right. Like I said, we're going to be dealing with exponents as we go. We're just the context of the problem changes a little bit. So the next section, R7, again deals with exponents, but it's going to put it in the context of a radical expression. What we're going to do, because we're smart like that, is we're going to take radical expressions and learn how to express them as rational expressions. The same thing we just talked about. Rational expressions with exponents. That's what we're going to do. We're going to take a radical expression, which means like a square root, a cubed root, a fourth root, fifth root, something like that, and learn how to convert that back and forth between the root notation and then a rational exponent expression out of that. And because we already know the rules for rational exponent expressions, we can work them out that way much easier. Okay. One of the things that you'll notice with mathematicians and math classes in general is we take things that are new and try to make them look like things we already know how to do. And that's the mark of a good mathematician, is taking something that's new and trying to relate it back to something that you've already done. So that's kind of what we're after here, is trying to be able to take something that looks different and relate it to past experiences. Good things for life. Relate something new you're facing with a past experience that you've learned from. What about life lessons with my high school students right now? They need a lot of them. Perfect. They have me for a teacher, and they're just teenagers, bless their hearts. So we have a cubed root, and here's how this works. Cubed roots, or any root, this is called an index, like index card, but index like in a number. Okay, an index, it relates to the denominator of the rational exponent. Whatever the index is out there, it's the denominator of the rational exponent. If there is an exponent in here, like this one, 27 has a first power, right? That is your numerator. Yeah, that exponent that's on the inside is your numerator. Okay, so index on the outside, whatever root you're dealing with, is your denominator of your rational exponent. The power that's on the inside, that exponent, is going to be the numerator of your rational exponent. So denominator on the outside, numerator on the inside. All right, so that means that we could rewrite this problem as 27 to the 1/3 power, which is similar to something we've already done. I think we may have actually done 27 already today. I can't remember. It's been a few minutes. But 27 we know is 9 times 3, right? And 9 is 3 times 3. So we really have 3 to the third power to the 1/3 power. And we can simplify that because we know exponent rules. 3 to the first power. 1/3 of 3, 1. Okay? So we're taking a root or a radical expression and converting it into a rational exponent because we already know how to work with rational exponents or are familiar with it. We've seen it recently out of that. What that does for you is it classifies anything with a radical on it as an exponent part of the problem. So in order of operations, square roots come before multiplication and division because they're exponents. That's the reason they come first. Cube roots in this case come before anything else because, or after parentheses, because of the fact that it is an exponent. So roots and radicals are exponents, and our job is to work with those in that form because it opens up all of these exponent rules that we already know how to work with, and it makes things much, much better when we have rules that work with. There are no such things as radical rules. There are plenty of exponent rules to work with or ways to work with exponents, but not many ways to work with radicals. Exponents are easier to deal with than radicals, and that's one of the reasons that we try to convert like that. Okay, let's look at this one. Fourth root. So the index is a 4. So that means when I rewrite this as an exponent, it's going to have what in the denominator? 4. Automatically know that because the index out here. Doesn't matter what number's on the inside. I'm going to put 10,000 in there. What do we know about 10,000? What's another way to write it? Maybe using 10 as a base. 10 to the what power? 1, 2, 3, 4. Remember how many zeros there are? That's what the exponent is. That may not be the prime factorization of that, but it is the shortcut. Anytime you got 10 or 1 in the front and a bunch of zeros after it, you can take that shortcut. Now, I put a 1 on the numerator of the rational exponent because I had a 1 exponent on the 10,000 to begin with. We rewrote 10,000 as 10 to the 4th power. And then our exponent rule says, hey, multiply those two guys together. What's 4 times 1/4? 1. So we end up with 10 to the 1st power. So we simplified that much easier. And kind of like we did with the other section, let's look at how we can put that into our calculator to get that. Your calculator has some neat features. One of them being a cubed root. It's not a button because you got to go through a menu to get it, but you can get a cubed root. One way is to hit the math button, and then you'll see there option number 4 is a cubed root. So you could pick that, and if I did the cubed root of 27 and just hit enter, it's going to give me 3 back. That's example A. That's what we did. Fourth root, it doesn't have a button for that. Okay, well, it does, but it's just as much trouble to get to. So you hit math, and then option number 5, and see it puts a blank right there. So you can put in the 4th root, and then I can press the right arrow key and then type in 10,000. And there I get my 10 out of that. So you can do those with that. I'm kind of lazy in the fact that I don't like hitting math button and then having to find the right piece. So I just use the reciprocal exponent rule and just say, okay, 27 to the 1/3. Because I can type that quicker. Normally, if I'm using my thumbs on the calculator in hand, I can do that lots faster than I can hit the math menu and remember which one it was. So I usually just use that conversion thing like we did it by hand out of that just because it's faster out of that. But your calculator can do a lot of strong things there in doing that. Negative 216. Let's put that under a cube group. Here's one of the rules of thumbs. If a index is odd and it's negative, so index odd and number negative, it'll equal a negative. If the index is even and the number is negative, it'll equal a non-real answer. Complex number. That's where the I comes back in, because square root's an even index. Remember what square root of -4 was plus or minus, it was 2i. That's where that comes back. That's a non-real answer out of that. So be able to recognize that. So here we get a negative number inside of an odd index. So we know we should be able to get a negative number back out of that. And you could type that in your calculator if you wanted to. I'm going to do the work here and say, okay, well, that's 108 and 2. I already knew that from last section. We did this same number, 9 and 12, 3, 3, 4, 3, 2, 2. So that's actually a -1 times 2 cubed and 3 cubed to the 1/3 power, which is just going to be -1 times 2 times 3, which is -6. That's what it equals there. But it's exponent rules there are kind of nice. But again, you can kind of do some stuff without that as you go along there. All right. Let's go into writing a rational exponent as a radical. So go in the other direction. So we've been taking these root expressions and rewrite them as rationals. Let's go the other direction, because there are times that does make it easier to do sometimes. We're all of these skills we're talking about in these first two sections are building up to some things that we can do to manipulate an equation and solve it. That's the whole point. Most everything that you learn in an algebra class that's like a skill like this is just so you can solve an equation that has that in it. Not that you're going to encounter equations like this a whole lot in life. Doesn't happen very much. But it's part of our curriculum, and the University of Tennessee says you got to learn this stuff. So they sign that check so that I'll teach you how to do it. So I'm gonna continue to do that. So because I kind of like them signing that check for me. So let's look at writing the radical expression. And we'll do several examples of this. We're not really working these out. We're just writing the radical expression that goes along with that. So what letter are we on here? D. Yeah, 16 to the 3/4. We're not going to work this one out. We're just going to rewrite it as a radical expression. So I know it's going to have a radical symbol. What's the index for this problem? 4. Where's that coming from? The bottom part of the fraction. What's on the inside? 16 to the 3rd power. So we've rewritten that in a radical expression. That's what I want you to do right here. I know we can do some work to simplify that, maybe, but we don't have to. Okay, all I'm after is rewriting it as a radical expression. Let's say we had a letter x to the 5/6. so that there actually is nothing we can do to simplify that. But we can rewrite it as a radical expression. What's the index? 6. What's on the inside? X to the 5th power. Oh yeah, this is fun stuff. This is easy stuff. Let's muddy the waters a little bit. 7 x to the 4/5. Can't let it be too easy for too long. What part of it has an exponent? Just the x. So the 7, does it go underneath the radical? Would he ask if it did?
It's gonna have to.
No, it doesn't. It doesn't have it doesn't have a rational exponent. I asked. Would I have asked if there wasn't some sort of exception for that? What's the exponent on 7? It's a 1. Notice it doesn't have a rational exponent. So it can't be under a radical. It's got to have a fraction exponent to go into the radical expression. So that 7, it's just going to hang out in the front. Well, he's not alone. He's pretty close. He's on the porch. I mean, you know. What's the index on the radical? 5. And what's inside? X to the 4th. So that 7 is just sitting out there in the front, waiting for this to simplify, and then it'll multiply times it, whatever it turns out to be. Okay. Now this problem's a little different. Got some parentheses in there. Now, does that 5 go inside of the radical?
Yes, because it's inside parentheses.
Because it's inside parentheses, that means that whole piece, 5x, has got a rational exponent. So that means it's going to go into an index radical of what? What's the index on the outside? 8th root of 5x to the 7th power. Notice I put the parentheses in there. It matters. Okay. Now, if I wanted to simplify that out a little bit and still have it as a radical expression, that x to the 7th, what's 5 to the 7th power? I don't know. I don't have that memorized. 78,125. I need a little more room there. Both of those are correct. But understand, sometimes they will go ahead and work out that number if it's not too large. If it were like billions, they probably wouldn't work it out. They'd leave it to parentheses stuff. But sometimes they will work that out. Sometimes they don't. So when you're looking on your Canvas quiz and you got parentheses 5x to the 7th power and that's not on there, they got these big numbers, well, they worked out that number for you on that. So sometimes they work it out if it's within reason. If it's too big, they usually don't. So, all right. Let's go the other direction. Let's take a radical expression and rewrite it as a rational exponent expression just to get that practice. So we're going to write as a rational exponent h square root or cube 7th root of the end of the 3rd. That's a good easy one to start off with. This is stuff we've already been doing today in this section. How do I rewrite that with a fraction exponent? Into the 3/7 power. And that's it. Good job. Let's put a number in there with it. How can you rewrite that? What's on the inside? Go ahead. Tell me exactly what to write. I think you're right, but I want to. So 10x, and then a 1/4 power, just like that. Where? Around the 10x. Why around the 10x? Yeah, because all of that is on the inside of that, so all of it should be on the inside of parentheses. So we could write it like this, or we could write it 10 to the 1/4, x to the 1/4. Realize that those are both the same thing out of that. This is probably the most common way of rewriting that, is that with the parentheses. But also this could also be the correct answer out of that. All right. With the 15 cube root of x to the 4th. (15x to the 4/3), like that, or do I need parentheses? Why do I not need parentheses on this one? Yeah, it's on the porch. The 15's on the porch. He's just hanging out there. Not allowed to vape in my house. So you got to do that on the porch. Another one here. (-2 5th root, parentheses, 3x squared to the 8. Ooh, fancy. So the (-2, where does it go? Like that? Is that what you're saying? And then 3x to the 2nd, 8/5. Yeah. Can we simplify that a little bit? How? (-2 times 3 to the 8/5, x to the 2 times 8/5, 16/5. This is probably the most common way with the parentheses and stuff, but also understand that this is also the same answer. It's just worked out a little further. Not that it made it very much better, but it is a little bit more worked out. All right. One thing that we've got to be conscious of is when we're simplifying radicals that have variables inside of them, because we don't know the value of the variable. If it's positive or negative number, we don't know that. So depending on what kind of index we have, what kind of answers we can get with those things. So we've got to be careful of those kind of numbers, and when we're simplifying those and solving some stuff. So if we're going to simplify, and let's just start with something fairly simple. What's the index on that when there's nothing written there? What symbol is that? It's a square root, so the index is 2. So they don't write it there ever, but it's really an index of 2. If they put a 3 there, it's a cubed root. But if there's nothing there, it's a square root, which is an index of 2. That's a little tricky thing about the radicals, that they, there's no such thing as a first root. because first root's just the same thing, right? This is that number
They
back.
put that 2 there, but it's understood.
It's understood to be there. Yeah, it's a square root. And square roots are, we're looking for square things, right? So that's an index of 2. So when we simplify this, we look at that and say, okay, well, that's x to the 6th to the 1/2 power, right? Or maybe a little better way would be x to the 6 over 2. That's kind of like what we were just doing. And 6 over 2 reduces to be x to the 3rd power. Now, here's where we've got to be careful. Because it was an even index, we need to put absolute value marks around our answer. So those are absolute value marks. The reason we need it to be absolute value marks is if it's an even index, what's the only kind of number we can get a real answer from when we take the root? Positives. And what does absolute value always give us? Positive numbers. Okay, so when we're simplifying with variables inside, we don't know what kind of numbers those are going to be. So that's where if it's an even index, that's the only time you've got to do it, is if it's an even index, put absolute value marks around your answer. Okay, even index. That number out here. Even index, absolute value. You got to remember to do that. If it's an odd index, you don't have to do that. For example, 7th root of x to the 14th. We rewrite that as a rational exponent to be x to the 14 over 7, right? Which ends up being x squared. Because it's an odd index, I don't have to worry about getting an absolute value mark on. Let's do a different number. Let's do x to the 20th on the inside. That way we get a different answer than some of them we've gotten before. Be x to the 5th, because that's going to be x to the 20 over 4, and that's where the x to the 5th comes from. And I need what on it? Absolute values, because it's what kind of index? Even index has got to have that absolute value mark on the answer when you simplify a variable. If it's a number, we don't have to worry about that as much because it's a number and we can actually work that out. But because it's a variable, we don't know what that number is. It could be anything, but what allows us to simplify it is the fact that we're making it, by putting those absolute value marks in there, we're making it into something that is positive. Let's say we had, did I skip a letter? I thought I did. Oh, well, who cares? As long as y'all know. The next example, whatever letter we're on, it doesn't matter. Is this one. 81, x to the 8th, y to the 10th, under the square root. So what's our index? 2 is our index, which turns into a 1/2 power. So that's going to give us, what's the square root of 81? That's something we know. It's 9. So we don't even have to do any work to get that. We know it's 9. And that's going to be x to the 8 over 2 and y to the 5 over, or 10 over 2. So it ends up being x to the 4th, y to the 5th, and I need absolute values on the y to the 5th. Technically, I should have absolute values on x to the 4th, but I don't have to write them because I know that anything to the 4th power will be what kind of number? If I take -2 to the 4th power, that's -2 times -2 times -2 times -2. It turns positive anyway. So technically, there should be an absolute value around the x to the 4th. It would be redundant to put it there mathematically, because I don't have to have it there because it's going to be positive anyway. So if you get to simplifying these out and you're putting absolute value around them all on the even index, that's not wrong. But sometimes if it's an even power left over, you don't have to have the absolute values. That you can just leave them like that and it be correct. Now that the fifth power with the y does have to be absolute value because it's an odd one. If I had -2 was y, -2 to the fifth power turns into a negative number, and I can't take the square root of a negative number out of that. So that's where you got to be careful of that. Now I'm just going to continue with my screwed up letters. It's okay. Just got to embrace the chaos here. Fourth root of -3 to the 12th power. That'd be -3 to the 12 over 4. Should be -3 to the third. Why did I put absolute values around it? It's the even index. Even though it's a number, we know that that's what's happening. But if I take -3 to the third power, I get -27. But it's in absolute values. That's really 27. That works out for me. There's one of those things. Kind of works that with a number to show, hey, this actually does matter, because normally we couldn't take the fourth root of a -27. We couldn't take the square root of a -27 and get a real answer. Fourth root, when you get into higher indexes or indices, is the plural for index. When you get into higher ones, it opens up the rules about negatives underneath there. Square roots, we're pretty locked into the square root of a negative number gets the I involved. When we get into higher powers, it opens up that vault of, depends on how it simplifies out, what it turns out to be. So the absolute values save us on that a lot. Do another. Fifth root of m to the 10th. M to the second, 10 divided by 5. Does it need absolute value marks? No. Index was what kind of number? Odd. So that's what tells us we don't need it. Okay. Easy enough. What if they throw something crazy? I mean, just bonkers in this. Let's say 3x minus 4 squared. It's still going to be 3x minus 4 to the 2 over 2, right? What's 2 divided by 2? 3x minus 4 to the first power is just 3x minus 4, huh? So it's crazy looking, but it's not that bad. It's actually, it simplifies out pretty nice. Where it gets looking crazy is when they do this. The square root of x squared minus 10x plus 25. And they say, hey, simplify that thing. And you're like, no, I can't do that. It's got addition and subtraction involved. So I can't take the square root of x squared because that's just part of that. But we look at that and we say, okay, one of these things is not like the other. It's much different than the problems that we've been doing, right? So if I think about problems that I've been doing, I need to think, how can I rewrite this with exponents? And the key to rewriting polynomials with exponents would be factoring those polynomials. So if we factor this polynomial, this one I'll do with the x method because it's 3 terms. Multiply to be 25 and add to be -10. 5 and positive 5 and positive 5. Positive 5 times -5 is -25. So negative would get me a positive 25 and a -10. So -5 and -5. x minus 5 and x minus 5, and Joe says, let's rewrite that as x minus 5 squared. Works out wonderfully because I know the index of this problem is a 2, so it's a lot like example S, or R, depends on if you skip the letter or not. And you have x minus 5 to the 2 over 2, which is just, and that big ugly problem up there that we started out with simplified down to just be a harmless little x minus 5. But it all came back from that simplifying by factoring. So anytime, if you see a polynomial inside of a radical of any kind, then you've got to think, oh, I bet I can factor that. Because you probably can. Okay. So think about factoring when you're doing that. All right. The next thing would be working with radicals in operations like multiplication and division, that sort of thing. So let's look at those. And we're still just simplifying. We're still doing that thing. So same section. I'm not changing sections yet. Square root of 5 times the square root of 45. So we think about that. And here's the rules for multiplying things with radicals. The index has to be the same for us to be able to multiply them together. If the index is not the same, then you can't multiply them together. Is the index the same on both of these? Yeah, they're both a 2 index. That's going to help us later on. But that also allows us to do this math. The math is outside times outside, inside times inside. So there's there's a 1 out here in the front. If there were other numbers there, you would multiply them together. 1 times 1 is 1. And then I'm going to have a square root of inside times inside, 5 times 45, which is, everybody knows they're 45's times tables, right? No, I don't. 225 is what it ends up being. Joe knows things. Joe knows everything. Well, it's okay. You don't go stupid. You can.
I know.
That's why I give you a whole week to do that, so that hopefully you're learning something as you go, and 2 times, so that you're learning something as you go. So hopefully you're picking up some. Yeah. All right. So what's the square root of 225? Is that a nice perfect square? It's 15. I always check that first, with my calculator, say square root of 225. If it comes out to be a decimal, then I know to do my factor tree and simplify if I can. But I always kind of check that first, especially when it gets to be a larger number, because I don't know those as spout off as I do. I can't lie, I knew that one, but it's not that big. Getting much bigger than that, I don't know them so well. 16 is 256. I know that because of computer programming. 256 is a big number. It's 2 to the 6th power, which is big deal with binary and stuff like that. But get past that, I'm a little iffy. Let's put some letters in there, so we got to actually use some rules. 5th root of n to the 3rd times the 5th root of n squared. Are the indices the same? They're both 5s. So that allows me to do the work of outside times outside, inside times inside. So that's going to be the 5th root of n to the 3rd times n squared, which would be n to the... What's the rule about exponents when I multiply? Add them, so that's going to be n to the 5th on the inside, which is better than n to the 6th, because now I know that because it's a radical expression, I can rewrite it as a rational exponent and just n to the 1st power is what it simplifies out to be. Now, that is kind of nice there. Now, I worked that differently than what was on my paper here, of the notes that I did last year. Last year I did this. Instead of doing this step, I did this step. Is that still legal?
Yeah, but I like the stuff you did.
I like the way I did it tonight better than I did the other one. Yeah, it keeps it all in a radical until the end, which usually will make it okay. Usually we don't work well with fractions is kind of the idea of that. So leaving things out of fractions until the very end. But it still ends up being n to the first power at the end because 3/5 plus 2/5 is still 5/5. So both of those ways work, but sometimes it's better to leave it as a radical instead of changing to rational exponents, just because it's easier. Oh, let's get a fraction in there because we don't like them. All right, when you're dealing with a fraction inside of a radical, the rule is split it apart. Whatever the radical is that's on the outside, it goes to both the numerator and the denominator. So it's a square root on this one, so it's going to be square root of 11 over the square root of 169. And then try to simplify those if at all possible, individually. Okay? The square root of 11 doesn't do anything. It stays the square root of 11 because I know 11's prime. That's how I know that. But what about 169? Does it have a nice square root? 13. So it works out nice. So we have square root of 11 over 13. How could I write that as a rational exponent? 11 to the 1/2 over 13. Those are equivalent expressions. One is with a radical, one is with a rational expression. But you're splitting it with the index that's on the outside. So yeah, I'm splitting it. It's on the 11 and the 169. I'm splitting it into both of them. Let's do this one. Maybe it'll make it look a little better. The 6th root of a over b to the 12th. I need a little b12. Right? Especially before math class. Split it apart. 6th root of a, 6th root of b to the 12th, and then try to simplify. One of the best ways to simplify is to think about it as in terms of rational exponents. So that would be a to the 1/6 over b to the 12 over 6, which reduces to 2, b squared, a to the 1/6. You could also write that as the 6th root of a over b squared. I'll scroll up so you can still see that. I had this problem, or similar problem. I don't think it was this exact problem, but it was similar to this that came up this week. Our high school students in Tennessee are taking the ACT test tomorrow for juniors. So we've been doing a lot of ACT math lately in my classroom. So a problem like this came up, and we hadn't gotten to this material yet in that particular course, and so they didn't understand the idea. But let's think about what we understand about rational exponents out of this. So on the inside, that part, how could I rewrite that as a rational exponent? It's 17 to the 4th index, so it's a 1/4 power, right? But it's all under a 5th root. And a 5th root takes that stuff that's inside of there and raises it to what power? (17 to the 1/4 to the technically 1/5). And we would get 17. Multiply those two together. 1 times 1 is 1. 4 times 5 is 20. That was the type of answer choices that it had on this ACT test. Is 17 to the 1/20th, and then it had 17 to the 13th power, and then like 17, something, had another fraction exponent in there. 17 to the positive 20 power was also an option there. But that student was like, what does that even mean? And I showed them what this does, and they I don't know that they understood it, but I think after a little bit of lesson they could, if I had time to teach that to them before the test. But I kind of explained to them, hey, one of those, because you haven't done that before, I would just basically put that in my calculator probably, and find out which one matched it decimal wise out of that. So yeah, I'll show you how. Great thing to know how to do. So we need a fifth root on the outside. So I'm going to hit math, and fifth root would be putting a 5 in that spot. And then on the inside, I need a fourth root. So I'm going to hit math again, and I'm going to put a fourth root on the inside. And then put a 17 in there. And that gets me that decimal. I worked it out with rational exponents and got 17 raised to the 1/20th power. That should be the exact same decimal. And it is. Okay. So you would be able to manipulate the numbers to decide which one is equivalent to what's going on there. Now, in the past, when you didn't have these nice graphing calculators, it probably wasn't doable. But it is a nice way of being able to check number problems here. Again, if it's got letters in it, you've got to know how to do the exponent rules, because your calculator can't do those. But if it's got numbers in it, then you can check some things out of that. Let's look at another one of those types of problems to finish off this section. Oh yeah, it was too close not to. All right, so let's think about exponent rules and how we could rewrite this one with a rational exponent. 8 to the 1/6, I heard. And then it's in a square root. So that would be 8 to the 1/6 to the 1/2. Multiply those two together. 8 to the 1/12. Or how could I rewrite that as a single radical? Eight to the first power there. Those are the same things. And again, you could type that in the calculator, see if that's the same decimal equivalent for that. You could actually simplify this one a little bit, because you've got 8 is actually 2 to the third power. So that'd be 2 to the 1/2 to the 1/2. Be 2 to the 1/4, which is the fourth root of 2. So that's actually the same thing as those two. So if you did the fourth root of 2, you get the same decimal as you get when you take 8 to the 1/12th power, or the 12th root of 8. Those are the same number. They look very much different, but they're the same number. All right, 2 sections down. Got 2 more sections to go. Yeah. The last 2 sections are solving equations for that. Let's take a short break. Let's take 5 minutes. Splash some water on your face, and then we'll come back and get these last 2 sections together. Okay.